All right, welcome back everyone to the deep dive. We're really excited for today's topic. We're always talking about the latest and greatest in machine learning, especially those papers that really make you stop and think. And well, today we've got one of those. This paper, it's called Actual Causation and Non-Deterministic Causal Models. And it's all about getting down to the nitty-gritty of cause and effect, but in a way that's super relevant to how we build and understand our models.
Yeah, this is a big one. I mean, think about it. In machine learning, so much of what we do is about prediction.
Right.
We build these models to predict outcomes. But really getting a handle on what's causing those outcomes, that's a whole other level,
Right.
especially when you're dealing with these complex systems we're always working with these days.
Totally. It's like we can build these incredibly powerful models that can do amazing things. But when it comes to actually explaining why they do what they do, things can get a little fuzzy. And
Yeah.
that's where this paper comes in. So what is it about this paper in particular that makes it so, groundbreaking? What are we really looking at here?
I think the biggest thing is that it proposes a totally new way of defining what we mean by actual causation. And it does this by taking a step back and asking, what is the role of this concept of actual cause in the way we learn and communicate our understanding of causal relationships? It's not just about defining causation in the world, but about understanding why we even care about the idea of causation in the first place.
So it's not just what is a cause, but what does the idea of a cause do for us? I like that. It's a really interesting shift in perspective.
Right. And to do this, the paper uses this framework called Non-Deterministic Structural Causal Models, or NSCMs for short. And these are, they're kind of like the standard deterministic models you might be used to, but a lot more flexible.
Non-deterministic. So meaning that things aren't always set in stone, there's room for multiple possibilities.
Exactly. They acknowledge that in a lot of real-world situations, the same starting conditions could lead to different outcomes. And that's something that traditional deterministic models kind of struggle with. And, the paper makes the case that this flexibility is really important if we want to get a clear picture of actual causation.
I see. So just to recap, this paper is giving us a new definition of actual causation, and it's doing it in a way that works for both our old school deterministic models and these new, more open-ended, non-deterministic ones. And the point isn't just to come up with some fancy definition. It's about figuring out what actual cause really means in the context of learning and building better models of the world. It's about using this concept to help us discover causes and make our models more streamlined. And the paper makes it clear that this new definition isn't just pulled out of thin air. It actually lines up pretty well with the author's earlier work on deterministic models.
Yeah, and that's really important, right? The fact that it kind of bridges these two worlds makes the whole argument a lot stronger.
For sure. Okay, so how does the paper go about laying all of this out? What's the game plan?
Well, they start by introducing these NSCMs, these non-deterministic models. And the idea here is to move beyond those limitations of the traditional deterministic models, which, like I said, assume that every cause has this single predictable effect, both in reality and in these what-if scenarios we use to think about causality. And they're very upfront about their main goal, to give us this new definition of actual causation that really utilizes these NSCMs and, importantly, is justified about how useful it is in practice when we're trying to understand and communicate about causes. They also point out, that defining actual causation and actually objectively judging those definitions, that's always been a bit of a headache. It often comes down to just whether or not you agree with the outcome of some thought experiment.
It's like those endless debates about who's really to blame when you come up with these crazy hypothetical situations.
No, exactly. So the paper lays out a very clear structure. First, they're going to formally define NSCMs. Then they're going to give us a kind of intuitive feel for why this approach makes sense. Then they dive deep into counterfactual dependence, but within these NSCMs. And that includes this interesting idea of interventional dependence. From there, they look at how we actually discover causal relationships, from a logical perspective, and how making our models simpler plays a role. And finally, they bring it all together and present their new definition of actual causation.
Okay, so let's unpack those non-deterministic structural causal models a bit. What are the key concepts we need to wrap our heads around?
So formally, an NSCM, it starts with a signature. And this signature includes a few things. First, you have your exogenous variables, which are basically the background conditions that we're not trying to explain within our model, like the stuff that we're just taking as given. Then you have your endogenous variables, and those are the ones we're actually trying to explain with the model. And then there's a range function, which just tells us all the possible values that each variable can take on. But here's the thing that makes them different from, say, Halpern's deterministic models. It's all in the structural equations. Instead of saying that like variable y equals some function of x, we say that y can be one of a set of possible values that are determined by its parents in the causal graph.
So instead of a single clear outcome, we have a bunch of possibilities.
Yeah, that's a great way to put it. And unlike some of those other deterministic approaches, this paper explicitly includes the causal graph, the directed acyclic graph, or DAE, as a fundamental part of the model's definition. This graph, it visually shows us the direct causal links that we're assuming exist between our variables. Then we have these concepts of a context, which is a specific set of values for those background exogenous variables, and a state, which is this set of values for the variables we're trying to explain. And a world is just the combination of a context and a state. And then a causal setting is basically the model itself combined with a specific world. The big takeaway here is that in these non-deterministic models, given those background conditions and the values of the immediate causes, there could be more than one valid way things could turn out. It's like, flipping a coin versus knowing exactly what's going to happen.
That definitely makes sense. It seems a lot more realistic for representing situations where there's randomness or where we just don't have all the information.
Exactly. Then the paper lays out the language we use to actually talk about these models. So we start with those basic statements like x has the value x, and then we can combine them with and or and not, the usual logical stuff. And then we have interventions, which we write as y, and that means we're forcing the variable y to take on the value y. And these interventions, they give us basic causal formulas like y-ur, which basically asks, would the statement be true if we intervene to set y to y?
So we've got our basic causal toolkit here.
Right. And then the paper goes on to define exactly when these statements are considered true in a specific causal setting. And they introduce two really important operations on the model: actualized refinement and the intervened model. So actualized refinement takes our general model and a specific observed outcome, and it basically updates the model's equations to match what we actually saw. It's kind of like calibrating our theoretical model with reality, And the intervened model, as you might guess, is what we get when we actually perform an intervention. We basically replace the usual equation for the intervened variable with the specific value that we set it to.
So if we saw that y ended up being 3, the refined model would reflect that. And if we imagined intervening to set y to 5, the intervened model would just have y equal to 5.
Exactly. And then the truth of that causal formula, like you, in a given setting, it's determined by looking at all the possible ways the system could end up after we've refined the model based on our observations and then perform that intervention. And then we just check if our statement is true in all of those possible outcomes. And the paper also touches on how to evaluate these statements in more abstract settings, where we don't have a specific observed world.
Okay, so we've got the language and the rules for interpreting it. How does this all lead us to a new way of thinking about actual causation?
And this brings us to the paper's informal motivation. They point out that the traditional way we try to define actual causation, it often boils down to some version of counterfactual dependence. Like that if X had been different, would Y have been different kind of thinking.
Oh.
But there are these really famous examples, especially those involving preemption, where our intuition tells us there's a clear cause and effect relationship, but that simple counterfactual dependence doesn't seem to hold.
You're talking about the Susie and Billy throwing rocks example, right? Where Susie throws a rock, it hits the bottle and it breaks, but Billy was about to throw his rock right after her. We'd naturally say that Susie caused the bottle to break, but if she hadn't thrown, Billy's rock still would have broken it. So it doesn't seem like the bottle breaking depends on Susie's throw in that simple counterfactual sense.
Precisely. And the paper argues that instead of constantly trying to adjust the definition of counterfactual dependence to fit these tricky cases, we should maybe take a step back and think about the real purpose of identifying actual causes. Like, why do we even care about this stuff?
So what's the paper's answer to that?
Well, they argue that it's all about the role that actual causation plays in helping us communicate and learn about these causal models efficiently. And they suggest that when we're not completely sure about all the details of a causal model, we often work with simpler, more conservative versions of it. And these structural simplifications, as they call them, they represent those models that are still possible given what we know, but they leave out some of the less certain or less crucial relationships. And the really cool insight here is that actual causal relationships might become clear through counterfactual dependence in these simplified models, even if they weren't obvious in the original, more complex model.
So by simplifying things, by getting rid of some of the clutter, the essential cause and effect connections become more apparent.
Yeah, that's the heart of it. And then the paper formally defines counterfactual dependence, but this time within these NSCMs. And they start with this standard definition adapted for non-determinism. So they say that Y counterfactually depends on X if in the actual world where X had the value X and Y had the value Y, there's some other possible value X for X that could have made Y take on a different value Y. But, and here's the key, they use the word might here, not would. And that might reflects the fact that we're dealing with non-determinism. It's not guaranteed, it's just a possibility. And they contrast this with a deterministic version, where Y would have definitely taken on a different value.
So it's that subtle but crucial difference between might and would that really highlights how non-determinism changes things.
Exactly. But I think the most innovative thing here is their introduction of interventional dependence. And this is where we look at dependence in a situation where we've already intervened to set the values of some other variables, like let's say Z to a specific value Z. And then we ask, does Y still depend on X in this modified model where Z is fixed? And this leads to both deterministic and counterfactual versions of interventional dependence.
Why is it important to make that distinction between regular counterfactual dependence and this interventional kind?
Well, because as the paper shows, these different types of dependence are super important for causal discovery, for actually figuring out the structure of that causal graph from data. For example, they have these theorems that show that if Y depends on X in this interventional sense, then X must be an ancestor Y in the causal graph. And even stronger, X directly causes Y if and only if Y directly depends on X in this interventional way.
So it's not just about observing what happens naturally. It's about actively poking and prodding the system to uncover its underlying structure. That's wild.
It is. It's like dependence isn't just a consequence of the causal structure. It's a key to understanding it. And then they get into this really interesting point about the difference between what they call intervention first and observation first statements in these non-deterministic models. An intervention first statement, it basically asks what could happen if we intervene in a world that's already the result of some prior intervention, maybe none. An observation first statement asks what could have happened if we had intervened differently in the specific world as we observed it. These two types of statements, they're equivalent in those standard deterministic models, but they can actually diverge when we have non-determinism. And the paper points out that this distinction is actually really similar to a well-established difference in Judea Pearl's probabilistic framework, between his due calculus and probabilities of counterfactuals. And that suggests that there's this deeper connection between these logical and probabilistic approaches when we start to embrace the idea that things aren't always completely determined.
It's like adding this extra complexity with non-determinism actually makes things clearer and connects different ways of thinking about causality.
Totally. The paper then moves on to what they call the logic of causal discovery, where they take this super idealized perspective and imagine that we can perfectly learn these interventionist statements of possibility. And if we make this assumption, which they call the exhaustivity assumption, that means we're assuming all possible outcomes are revealed through experiments. If we do that, we can actually start to figure out part of the causal graph. But to get the complete picture, we need to know about counterfactual dependence, which isn't fully captured by those interventionist possibilities.
So this is where the idea of simplifying the structure of our models comes back in, right?
Exactly. They argue that this exhaustivity assumption is often too strong to be realistic, and they propose that we replace it with a simplicity assumption. And this assumption, it favors causal models that are simpler in two ways. First, they have fewer possible outcomes from interventions, what they call inset simplicity. And second, they have a simpler underlying causal structure, which they measure by the ancestor-descendant relationships in the graph. The most normal models under this simplicity assumption, they're the ones that are both structurally the simplest and have the fewest possible intervention outcomes. And they call this the default model. But then there are these other less normal models that are still structurally simpler than this default one.
And these are the structural simplifications that the paper's been building up to.
You got it. And they actually provide a formal definition for when one causal graph is a structural simplification of another. It's essentially a subgraph where any edges that have been removed, while removing them, also corresponds to the removal of ancestor-descendant relationships. They also define what it means for one model to be an interventional extension of another, which means that all the possible outcomes of interventions in the first model are also possible in the second model. And finally, they give a formal definition for one model being a structural simplification of another, which takes into account both the graph structure and how their underlying equations relate to each other. So basically, when we simplify the model by removing a causal link, we got to reinterpret how that affected variable is determined, based on its remaining causes and considering all those possible influences of the removed cause. They then prove that a structural simplification is always an interventional extension and that it has this minimality property when it comes to further simplifications and extensions. The takeaway here is that if we're going with this simplicity assumption, the causal models that we should think are plausible are structural simplifications of that initial default model.
Wow, that was a lot to take in, but I think I'm following. So we've built up all this foundational stuff. Finally, how does the paper actually define actual causation using these ideas?
All right, so here's the big idea. Actual causation, according to the paper, it corresponds to the weakest statement of counterfactual dependence that can actually challenge our weakest assumption about the true causal structure. And our weakest assumption is that the true structure is one of those structural simplifications of our default model. Okay, so formally they define it like this. X, having the value X, is an actual cause of Y having the value Y in a specific causal scenario, if there exists a structural simplification of that scenario where Y having the value Y counterfactual depends on X having the value X. And a really important point they make is that this simpler model, well, it can also be a structural simplification of the original, more complex model itself. So instead of looking for counterfactual dependence in the full, potentially super complicated model, we look for it in simpler, more plausible versions of it.
So it's not what if things were different in this exact complex situation. It's more like, is there a simpler way to look at this where we can see a clear, if not X, then not Y connection?
Yeah, you got it. And the paper argues that this definition, it really aligns with the reason why we want to understand actual causation in the first place, especially in the context of learning. It works for both deterministic and non-deterministic models. And, this is a big one, it largely agrees with the author's previous work on deterministic models, which means it gives us reasonable answers in a lot of those tricky examples that we talked about before.
Like Susie and Billy. One last time, how does this new definition play out in that scenario?
So in that late preemption example, they show that if we consider a structural simplification, where we get rid of the direct causal link between Billy's throw and the bottle breaking, we end up with this non-deterministic equation for whether or not the bottle breaks. And in this simplified model, if Susie hadn't thrown her rock, the bottle might not have broken. And that right there, that establishes the counterfactual dependence of the bottle breaking on Susie's throw in this simpler model. And that means Susie's throw is an actual cause. But even if we look at those simplified models where Billy's throw could still be a potential cause of the bottle breaking, we don't see that same counterfactual dependence of the shattering on Billy's throw, given that Susie did throw. It's almost like this approach formalizes our intuition to just ignore that preempted backup cause when we're trying to figure out the actual cause. And the paper points out that this new definition doesn't have some of those problems that older definitions had with irrelevant factors, like how accurate Susie is at throwing. The new definition is more stable. It doesn't change its verdict based on those less important variables.
I love that. It feels like this approach really cuts through the noise and gets to the heart of what matters. So this is a pretty big deal, right? The different way of thinking about actual causation. We're moving away from just our gut feelings about specific examples and towards this more functional and philosophical way of thinking about it. So where does this leave us in the bigger picture of machine learning?
Historically, in machine learning and related fields like causal inference, we've built these sophisticated tools for finding statistical dependencies and even building causal models from data. But when it came to actually figuring out the actual cause of something specific, we often relied on these more philosophical arguments and, our intuitions about what we thought a cause was in a given situation. And this paper, it offers a more grounded approach, a way to connect the definition of actual causation to that process of learning and refining our understanding of causality. And it suggests that a big part of understanding causality is being able to build and reason with these simplified models.
So it's not just about building a super complex model that fits all the data perfectly. It's about figuring out which parts of that model are really essential for explaining specific outcomes.
Exactly. And this has huge implications for explainable AI. Instead of just saying feature X was important for this prediction, we might be able to say the actual cause of this prediction within a simplified but still plausible understanding of the model was a specific change in input Y. And that could give us much more useful and actionable explanations.
Okay, awesome. Now for our favorite segment, novel notions. Based on what we've learned from this paper, and especially that focus on structural simplification, what are some cool research directions this could lead to in the world of machine learning?
All right, so one idea that I think is really interesting is developing algorithms that can automatically discover the most relevant structural simplifications. The paper gives us this great theoretical framework for simplification, but doesn't really tell us how to actually find those simplifications that are the most informative for understanding the causes of a specific event, especially in a machine learning model that we've already learned. Imagine we have like a really complex Bayesian network or a structural causal model. Could we build an algorithm that systematically explores all the possible ways to simplify that model, maybe by removing edges or grouping variables together, and then pick out those simplified models where we see clear counterfactual dependencies for the outcome we want to explain?
But how would we even define what relevant means in that context?
Yeah, that's a huge question for future research. We could say that relevance is based on how strong the counterfactual dependence is in that simplified model. Or maybe we could use some prior knowledge or constraints about which causal relationships are more likely to be important in a particular area. Like, imagine we're simplifying a model for a medical diagnosis system. We might want to prioritize those simplifications that preserve known biological mechanisms. And we could even think about the cost of interventions in the real world. Maybe we favor simplifications that remove those relationships that would be hard or unethical to actually test. It could really connect the work that's being done in interpretable machine learning, which often focuses on feature importance, with the more in-depth understanding of causality that we get from structural causal models.
An AI system that not only learns a complex model, but can also simplify it in a way that makes sense causally to explain its own behavior. That's a really cool idea.
Yeah.
What else could we explore based on this paper?
Well, another direction, building on the paper's emphasis on those non-deterministic causal models, could be to actually incorporate non-determinism into our machine learning models and causal inference techniques from the get-go. Right now, a lot of the methods we use are still kind of stuck in that deterministic mindset. What if we built models that were better at representing those situations where multiple outcomes are possible? It might involve exploring new types of model architectures or coming up with inference methods that can work directly with these non-deterministic representations.
How would we actually use those kinds of models in practice?
Think about those messy, complicated systems in the real world, like modeling how a disease spreads or trying to predict the stock market. Instead of trying to force everything into a single deterministic model that captures every detail, we could build a non-deterministic model that captures the range of possible outcomes and how likely each one is. Then, when we want to understand what caused a specific outcome that we actually observed, we could use this whole idea of structural simplification within that non-deterministic model to pinpoint those factors that made that outcome more or less likely to happen. It could give us much more robust and nuanced causal insights in areas where those deterministic models often just don't cut it. And it could connect to research on learning causal models from data that's noisy or incomplete, where non-determinism might be a more natural way to represent that uncertainty.
Wow, those are some great ideas. This paper, by tackling such a fundamental question about causality, has really opened up some exciting new avenues for research in machine learning. For those of you who want to dig deeper into this, check out the link to the paper in the show notes. This has been a fantastic deep dive into the world of actual causation.
I agree. It's a good reminder that as we create more intelligent systems, we need to really understand cause and effect.
Absolutely. Thanks for joining us on the deep dive. See you next time.